So let's do some conservation of angular momentum. Here's the story. So this is one of those merry-go-rounds that you have at parks. There's little safety bars that come out, and you can hold on to the bar and then spin around on this thing and try not to throw up. And here's an older sibling and the younger sibling, and the younger sibling has a mass of 10 kilograms. Now, what the younger sibling wants to do is be dropped down just as that bar is right in front of him, so he can grab onto it and then spin around on this merry-go-round. And let's see. Let's have the merry-go-round initially rotating at, let's go, I don't know, 15 rotations per second. Oh, that's horrible. Let's go with 2 rotations per second. That's still fast, but it makes the math a little easier. So he's rotating at that rate, or the little merry-go-round thing is going at this 2 rotations per second, or radians per second rather, and the little boy is not rotating at all. So we want to know how fast the merry-go-round is going to go after the little boy is dropped on and he safely grabs on. He's not injured at all, but he's going to hold on at the very edge. So let's think about this. In the first quarter of physics, when we did anything with collisions, we had two things, or two topics that we talked about. We had inelastic, and elastic collisions. Where you go? Can you? An inelastic collision, remember, just means that they stick. So this would be, this turntable in linear world would be if the mass was just kind of moving along a line and then hit a glob of clay or some dirt or whatever the case may be, and in the end the car and the glob of clay move in a linear fashion. An elastic collision, remember, would be if the blob of clay that the cart hit bounced off. So we used billiard balls for those examples in the first quarter of physics. Now it's the same thing. So if something sticks, then we are looking at an inelastic collision. So remember, we're still going to have then momentum before. Let me define this real quick. So a momentum initial is going to be conserved to equal momentum final. And in the last video you watched, our translation going from linear momentum to angular is that just instead of mass times velocity, now we have this moment of inertia times, and we'll call that 1 times omega 1 is going to equal my inertia, moment of inertia in the end, times my new omega. And these can be very generalized, because I could have, just like my billiard balls, I could have 2 things that are spinning initially, and I could in the end have them stick to where I would be combining my inertias, and so then I'd have 2 different omegas. I'm sorry, I'd have the same omega. Or I could have 2 things spinning and then they bounce off of each other, so I'd have their independent inertias with their final omegas. So we can look at those different quantities. But for now, let's just kind of focus on this one, and in lecture this week, we'll do the bouncing off thing so we can see how much fun that is. And we can combine, you had to see this coming, we can combine energy and momentum once again. Yeah, and in that way we can solve for final omegas, because we're going to see if it's elastic, that we end up with too many variables. But for now, let's just focus on how fast the boy ends up going with the merry-go-round once he lands on it safely and securely. So here's the fun thing. We're not going to treat the boy's mass or his inertia as any kind of shape that we need to do anything with. We can treat his inertia, so inertia of the boy, as a point mass. not a point particle, but a point mass. And so his inertia is just going to be his mass times the radius squared is the distance from his axis of rotation. Okay. At some point, we can start approximating everything and anything as a sphere, and that becomes fun because it makes no sense to anybody. Anyhow, so he's going to stick there. So the radius here, if he's on the outside edge, is going to be this 3 meters. So his radius, or the radius where he is at, is this 3 meters. And now for the, whatever the heck that's called, merry-go-round, then this one has an I wrote up top of 1/2, so its I is 1/2 mr squared. And I gave its mass and everything there. So let's see how this looks. So I have initial of the, or my inertia of the merry-go-round initially, times its omega, so that's my mv, and it's going to go in the end to the inertia of the boy plus the inertia of the merry-go-round times our omega final, so our omega initial. So then I can rewrite this. If all I want to do is get to the omega final, then I have my inertia for the merry-go-round times its rotation divided by the I of the boy plus the I of the merry-go-round. And so this makes sense. I mean, just like before when we looked at things moving linearly, if they stuck together, maintaining velocity seems like that would be rather difficult to do unless I have some sort of exterior force happening, right? And then when we have something external force, not exterior, I guess it's the same thing, but if I have an external force acting on the system, then remember, then we're looking at conservation of momentum from that split second, that really fast moment just after the collision. Okay, so ignoring friction or anything that's going to slow this thing down. All right, so now let's put in our inertias. So I have my 1/2 75 kilograms times my r squared, 1/2 mr squared, yeah, 3 meters squared, times the mass of the merry-go-round, which is 75 kilograms. So this is my I, 1/2 mr squared. Whoops. Why did I do that twice? I don't know. Don't do that twice. And now my omega naught. So my rotation is 2 rotations per second. Cool. Now, let's think about what's happening on the bottom. The I of the boy, well, we've just made him mr squared, so we have 10 times 3 squared plus, and I get to repeat this same process, or the same moment of inertia for the sphere. So 1/2 75 kilograms times the radius 3 meters squared. Sweet. Now before I button push anything, I look at this and I'm like, I have a 3 in this term, or 3 squared in this term, 3 squared in this term, 3 squared in this term. My 3 squares are all going to cancel out. So just a little less button pushing, so I'm going to end up with 75 times 2 divided by 2 times 10 plus 1/2 times 75. Oh, I can go ahead and distribute that and simplify this more. I'm a really big fan of doing that so I don't have to put a bunch of stuff in my calculator. So let's see, I have 150 divided by 20 plus, oops, when I distribute that, that just becomes 75. So in the end, I have 150 divided by 95. Much easier to put in. So 150 divided by 95 tells me that it slows down to 1.58 radians per second. Radians. Rotations, I'll be consistent. Rotations per second. Cool. So once it sticks, I have slowed down by that amount. I started off initially, remember, at 2. Whoops, you can't see it. At 2. And then once the little boy lands, the rotation slows down by almost a half. Pretty cool. So the process is just the exact same. That's the point I wanted to make here. That everything that you did with linear as far as momentum goes is going to be the same here. The only thing we're doing is replacing our masses with our moments of inertia and replacing velocity with omega. Awesome.